Hello everyone, I'm John Daniel from Peking University. Today I will present our work, Andron PTM, a scalable and economical large-scale pre-training system in Tencent. And our collaborators are coming from Peking University and Tencent. In recent years, we have witnessed a paradigm shift in machine learning, marked by the rise of large-scale pre-trained models and their impressive performance across a variety of tasks. Numerous transformer models have been developed, achieve state-of-the-art performance in diverse domains, including computer vision, neural language processing, speech recognition, multimodal, and protein structure prediction. OpenAI have proposed scaling laws for neural language models, motivating researchers to scale their models for improved performance. Specifically, their observations are illustrated in two figures. The left figure shows that large models achieve better model quality under the same data volume. The right figures show that large models require fewer computation budget to achieve the same quality. To sum it up mathematically, the model quality is proportionally to the number of parameters it has. The amount of data is trained on and the computer results allocated for training. Thus, the trend of continuous growth in model size will continue, which would pose challenge and put pressures on the underlying GPU hardwares. While scaling laws suggest that bigger is generally better for model performance, there are practical limitations and challenges that cannot be ignored. The first one is growth in computational requirements for models significantly outpace the GPU performance improvement. The second one is the growth in parameter size for models significantly outpace GPU memory requirements. So how can we train this large model efficiently and economically? The solution lies in distributed training, which involves multiple GPUs to accommodate large models and accelerate the training process. However, there are two mainstream strategies for distributed training, data paradigm and model paradigm. The question then arises, how do we choose between them? We initially investigate the key tasks associated with large-scale model training at Tencent, which can broadly divide into pre-training and fine-tuning. The pre-training phase is to extract word knowledge from the large training datasets. We train large models on hundreds of GPUs for several weeks, which accounts for 10% of total tasks. The problem of this phase is the high frequency of server downtime during long-term training on large-scale clusters. So the design requirement of our system is to be simple and efficient in scaling with dynamic change in the number of machines. In the fine-tuning phase, we align the model with a specific downstream task. We train large models on hundreds of GPUs for several hours, which account for 19% of total tasks. The problem of this phase is the low GPU utilization due to the small volume training, some of available training data, and a large number of GPUs. The design requirement of this phase is our system needs to minimize resource requirement for each task to improve the overall resource utilization. Based on the analysis of this task in Tencent, we have identified two key characteristics essential for our productive deep learning system. The first characteristic is easy to use and easy to scale. Considering that users often lack the specialized knowledge required for distributed training, our system should be designed to allow distributed training with minimal code changes. Moreover, our system should scale seamlessly across any number of GPUs to ensure easy fault tolerance. To address this, we have adopted the data paradigm approach. The second characteristic is efficient and cost-effective. Our system aims to make the best use of GPU results for both pre-training and fine-tuning tasks, and minimize result requirements to improve overall utilization and accessibility for fine-tuning large models. To achieve this, we have adopted parameter sharding to reduce the the unnecessary parameter storage and involve hierarchical memory to increase the number of GPU required for fine-tuning large-scale models. The workflow for hierarchical memory, training on hierarchical memory is illustrated in the right. The GPU fetch the parameters from CPU and perform forward and backward computation on the GPU, and then send the calculated gradient back to the CPU. The CPU loads optimizer states from the SSD storage. From optimizer updating on CPU and store the optimizer states on SSD storage. While other systems also have adopted similar strategy, they exhibited three inefficiency, including inefficient memory utilization, inefficient bandwidth utilization, and inefficient GPU utilization. To mitigate the various identified inefficiency, our system employs the attribute of persistent parameter storage and the iterative nature of deep learning training paradigms. The concept of persistent parameter storage refers to the idea that parameters are neither regenerated nor released. Rather, they are simple transfer between different storage. As a result, this allows for efficient management of multi-level parameter storage. The iterative nature denotes that the process of deep learning training is iterative. The characters allow us to predict the execution sequence and the timing of each operation in the subsequent training run. Based on this consideration, we introduce three optimization design, including fine-grained page-based memory management, a unified scaling-based tensor, a unified scheduler based on tensor lifetime, and the log-free updating mechanism. The fine-grained page-based memory management is proposed to solve the existing issue, including the inconsistent tensor size, make direct memory reuse unfeasible, and the frequent allocation and deallocation lead to loss of fragments. The other issue is large tensors cannot be transferred even available GPU memory is hundreds of million bytes. We show the distribution of tensor size with one layer of GPT-3 in the table. Our solution is manage the tensor at the page level, including allocate, free, move, and communicate. We split large tensors and merge small tensor into pages, and thus these pages can be directly reused. The optimal page size is set as 4 million bytes. The second component of our system is the unified scheduler based on tensor lifetime. Because the existing system schedule distributed model across the heterogeneous storage and schedule the computation and communication and data transfer without considering the real workload. So our solution is use the tracer to track each tensor lifetime, leveraging the iterative nature. We first store parameters in GPU memory and optimize states in CPU memory and SSD. And we implemented a dynamic cache to reduce the data transfer. Based on lifetime, we make decisions of transfer and communication timing to maximize the overlap between compute and communicate. Finally, we adopt the log-free updating mechanism to reduce the bottleneck by CPU optimizer. We show the timeline of original SID training, where we can see the almost time from the SID input and output and the CPU optimizer. Thus, we introduce a log-free parameter updating mechanism by maintaining a CPU buffer for parameters and gradients to decouple GPU computation from CPU optimizer updating. Our experiments are conducted on a production-grade GPU server, GPU cluster, including 96 servers. Each has 8 NVIDIA A100 GPUs. We conduct evaluations on 3 large-scale transformer models, including GPT-3, T5, and T5 MOE. The first metric is the maximum model scale. Compared with the DeepSpeed, our system can support larger models using the same hardware results and achieve higher training efficiency for the same model scale. As for the system efficiency, our system consistently outperforms framework systems such as DeepSpeed and Metro. For the scalability experiments, to verify the scalability of Android PTM, we conduct evaluation on 2 extreme large-scale transformer models, including GPT-3 and T5 MOE. We achieve super linear scalability when training with the GPT 175 billion models because we set the experiment at a weak scaling setting. We also achieve near linear scalability when training the T5 MOE models. To support extreme model scale, we utilize the SSD storage into training. We achieve near linear scalability when training models with SSD on Android PTM. By leveraging the log-free updating mechanism, Android PTM improve overall throughput by 2.96 times with little impacts on model quality. Thank you all for your time and attention. To conclude, we first analyze the characteristic and requirement of large-scale model training task in Tencent and propose the underlying design of Android PTM to address this requirement, which integrates data parameter sharding and hierarchical memory. To reduce the memory fragment and fully utilize the memory bandwidth, we propose the fine-grained page abstraction and manage the model state at the page level. Furthermore, we design the unified scheduler together with a fine-grained lifetime-based scheduling method to dynamically manage this operation in a holistic manner for efficient training. To support enlarging models to an extreme scale, we integrate the SSD storage and design log-free updating mechanism to eliminate the bottleneck of SSD input and output bandwidth. Finally, we implemented our system Android PTM on top of PyTorch and verify the superiority of our work through comprehensive experiments. Thanks for listening.